Number Theory, Section 4, Diophantine Equations. Video 5, Other Diophantine Equations. Here are some famous examples of Diophantine equations. First of all, Fermat's last theorem, which considers what happens with a to the n plus b to the n equals c to the n in the case where n is greater than 2. Now, when n equals 2, you should recognise this as being Pythagoras' theorem, a squared plus b squared equals c squared. Fermat very famously conjectured in the 1600s that for any value of n bigger than 2, there were no solutions to this. This remained unsolved until Andrew Wiles proved it in the 1990s. If you've never read that story, it's very worth looking up and finding out a little bit more about. Secondly, the Erdős-Strauss conjecture, which states that fractions of the form 4 over n can always be written as the sum of 3 unit fractions, 1 over a plus 1 over b plus 1 over c, for n greater than or equal to 2. Now, this is still an open conjecture. However, computers have verified that this is true for some very large values of n. Finally, Euler conjectured that a to the 4 plus b to the 4 plus c to the 4 equals d to the 4 has no solutions. And unfortunately, Euler's conjecture has been proved to be false. Computers have found some very, very large values of a, b and c that satisfy this, but this wouldn't really have been possible for Euler to prove with the calculation methods that he had available to him. Now, you're not going to be expected to prove open problems in number theory as part of this course, but you are going to be expected to solve things that have a similar flavour to some of these equations. So perhaps things that have been inspired by some of these results. Let's have a look at an example. So write a program to find all the solutions to the Diophantine equation a squared plus b squared equals c cubed, where a, b and c are less than or equal to 50. And then using our solutions, show that a given solution, if c is equal to a, then a is one more than a square number. So let's have a go at writing a program first of all. I'm going to start by defining a function. I'm going to call it dio for Diophantine, and I'm going to take an input n. I'm going to put in n equals 50 to check the cases up to 50 as I have been asked to do. So for I in the range from 1 up to n plus 1, and for j in the range from I up to n plus 1, and for k in the range from 1 up to n plus 1, I'm looking for values where I times I plus j times j is equal to k times k times k. Or I could write that as k cubed, like that. And if it satisfies that, I want to print out I, j and k. So let's see if I can find anything in the range up to 50. And it's given me 2, 2 and 2. So 2 squared plus 2 squared equals 2 cubed. 2 squared plus 11 squared equals 5 cubed. So I can check that. 2 squared is 4. 11 squared is 121. 121 plus 4 is 125, which is 5 cubed. So it's found quite a few values there. So let's have a look at that program again. So you can see that I've gone from I in the range 1 to n plus 1 and j in the range from I to n plus 1. That's because my a squared plus b squared, it doesn't matter which way around they are, so I is the smaller of the two and j is the larger of the two. And if I put 1 there instead of I would get solutions being repeated. And then k is going from 1 to n plus 1. That is going to be my cubed value. So if I times I plus j times j gives me k to the power 3, print out I, j and k. Now you might be thinking back to the video earlier in this section where we looked at Pythagorean triples, and we looked for a square number by doing the square root. And you might wonder why we haven't looked for cube numbers by doing the cube root. You have to be very careful with rooting things in Python because you're not always going to get exact answers. There might be rounding errors, and the rounding errors, once you're cube rooting, come in quite quickly. So this is a safer way of doing it to make sure that I don't get any rounding errors that mean that I miss solutions. Now, the next part of the question asked me to think about what happened when A was equal to C. So let's have a look at some of the examples here. So A is equal to C here, and A is 2. And A is equal to C here, and A is 5. A is equal to C here, and A is 10. So in the cases that I've got where A is equal to C, A minus 1 is a square number. A is 1 more than a square. 2 is 1 more than 1, 5 is 1 more than 4, and 10 is 1 more than 9. So the examples that I've got so far certainly satisfy that if C equals A, then A is 1 more than a square. How would we go about proving this? Well, I'm told that A equals C, so I can rewrite my equation as A squared plus B squared equals A cubed. That rearranges to give B squared equals A cubed minus A squared, which means that B squared is A squared times A minus 1. Now, in order for this to be a square number, all of this has to be a square number. This is already a square number, so A minus 1 is a square number. So A is 1 more than a square. Let's see that written out neatly. So if A is equal to C, A squared plus B squared equals A cubed. B squared is A cubed minus A squared. B squared is A squared times A minus 1. So A minus 1 is a square number. So A is 1 more than a square. In this video, you've learned some examples of famous Diophantine equations, and you've learned how to write a program to search exhaustively for solutions to a Diophantine equation in a given range.